For those of you who don't know me, I'm Magnus Melander. I'm a co-founder of Things together with Linda. 6 years ago we started this place. We were hit quite badly by the corona train in March. We survived, and we have changed quite many things in how we operate, in our effort to enable collaboration between corporate-ready innovation companies and corporates, because that's what we do here. And one thing we agreed early in the summer was there is no way that digital-only events will work. We're already sick and tired of those. We just have to get back to meeting in real life. Because one thing is to make presentations, like Melissa, Alexander, and Sebastian will do, which is easy to put on video and share and all those kind of things. We can do all of that, and we will do all of that. But to meet people and to challenge them and get inspired by them and so on, that's really the other value that we cannot forget. So we're going to do smaller, we try now, we do smaller events with fewer people. We stick closer to the members of Things, both big and small companies, because we can't boil the ocean any longer. Not even we can do that. So this is the first time we try a smaller event in the real world, and I'm proud of you guys, because so many people have talked to say, yeah, I would love to come, but I'm not allowed to. Or, I would love to come, but I don't think, I'm sure my wife will appreciate that I go, or my husband. You know, there's all kind of reasons, which I accept. You know, people have to live their own lives in this and cope with this. But I'm so happy to see you guys here. And we have measured very carefully the distance between the seats, backwards, forward, and so on. So everything should be under control. So without any further ado, we have an anniversary today. This is the 10th Get on Top of Machine Learning event. Can you believe that? And I'm sure that some of you guys have probably been on every single one of them. I think Alexander is probably the most likely candidate. Yeah. No, it's quite amazing. It became something like you just had to be there to see what the others was doing and what happened since the last kind of quarter or so, and it became very good. So today we did it a little bit different. We have only 3 presentation companies. We're going to spend about an hour together with them on stage, and we're going to try to, as an anniversary thing, we're going to try to talk a little bit more about what's going on and what's happening and what can we expect and so forth. And among us we have companies who just changed the business model, for instance, which is quite interesting. So that's what I expect out of today. And obviously, if the crowd has questions, please raise your hand and jump into the discussion. And if you do, please present yourself so we know who's talking. So, with that, let's start with Sebastian.
Thank you so much.
One of the incredible companies who stayed with us during the whole Corona episode at the co-working space here. Take it away.
Thank you. So my name is Sebastian Gaidi. I'm CEO and co-founder of a company called Greenlytics. So we work with weather analytics targeting the power industry. We sit here at the 2nd floor. And by the way, so I will present a little bit about the stuff that we do around machine learning. Feel free to interrupt at any point. I rather have like a more dynamic discussion than just a pure presentation. So this was me in 2017. I was working as a power trader in a big utility company. And as a power trader, you're bombarded with data. And your job is, as a human, to kind of grasp all this data and drive decisions in the city. So data from the assets, so the power plants, data from the power lines, data from the markets, and also weather data. And with the introduction of renewables, you have a big change, transformational change in the energy system. This is becoming much more weather dependent, and that's a big challenge. And if you're kind of a little bit analytical oriented and like to think about data problems, then you see that this is a very interesting data problem for any data scientist to dig their hands into, and that was exactly what we did when starting Greenlytics 2 years ago. So basically, we've been working on specifically is a project on wind power forecasting, and I'll just dive into exactly how this is done. So we take in meteorological data. So there's this big, large supercomputers that run meteorological models. We take this output from these models, And then we make a middle layer with some machine learning model, and then we try to predict actually how much wind power will be produced in order to be able to balance the grid, trade energy, and keep the balance despite this increase in renewables. Short company background, so our kind of niche with Greenlytics is that we kind of try to combine data science, energy system, and metrology. So these kind of knowledges. And as you know, as a data scientist, it's really always about the application. So what are you working on? So if you don't know what type of application you're working on, what's the physical background of that, then it's very hard to actually solve a data science problem. So we are very niched on that. This is our team. So me, up there to the left, my co-founder behind Hero, who's a technical guy. So I'm using doing the business pitches, but now I'm on technical stage today. And then we have 2 PhD students from KTH and 2 developers. So today I'll present a little bit about machine learning for solar and wind power forecasting. And basically just to introduce the problem. So we have a time series. And then what we want to do is try to predict this time series each steps into the future. So regression problem. But really, actually we don't just want to have a point, we usually want to have some uncertainty, because there's always some uncertainty involved in this process. So we can formulate that kind of mathematically. So we want to estimate a function, f, given some information set, c, and then we are given all these marginal distributions over these time horizons. And this information set can consist of several different types of variables. For example, autoregressive variables. So maybe these ones here are good predictors for what's going to happen next. We can have explanatory variables, such as the wind speed at that site. And then we can have forecasted explanatory variables, so the forecasted wind speed at that particular site. Just short on error versus uncertainty. So I think you maybe know about this already. But some actually confuse this. So with uncertainty I mean actually something that we haven't observed yet, but is the likely distribution of the errors that we would have observed. So it gives the range of the error given a model. Okay, so. Actually, I will skip this to save a little time. So, what we looked into then was this challenge. So, when we start with a machine learning problem, it's very interesting, to see what have other done. And the best way I think to do this is really to Kaggle challenges. And we found this challenge, which is quite niched and on to the spot on what we're doing. Which was held in 2014. And this was not a Kaggle, but was a different platform, Crowd Analytics. So basically they provide a data set to benchmark models, and that's exactly what we did. We also found a paper, a very interesting paper, that went through all the winners of this challenge to see what were the best participants in this competition. And here you have the top entries in the win track. And if you look at the top 2, so everyone usually on this kind of event speaks about neural networks and image processing and all great things that you can do with that. But actually here you see no neural networks. It's actually other types of machine learning models, decision trees. So that's actually what I will talk a little bit about today, but a specific type of decision tree, which is called gradient boosting decision tree. So just to know, how many have heard about gradient boosting decision trees before? Okay, about half. So there are 4 different, at least in Python, implementations of, or known implementations, or popular implementations of gradient boosting decision trees. We have XGBoost, that is very popular. That's gained a lot of traction on Kaggle because of winning a lot of competitions on tabular datasets. We have ITVM that actually did what XGBoost did, but even faster with some approximations. We have CatBoost that was launched by the Google version, the Russian version of Google, Jenkins, and then we have the scikit-learn version, which is actually the first version of the launch. So what is a gradient boosting decision tree? So we can think about this as a problem where we have a group of people, a family, if you wish, and what we want to predict is their likelihood of liking a computer game. And then we can think about different input variables like age, gender, occupation, etc. Then we try to split up this group at different intersections or different points in this feature space, where it actually gives better predictions for the outcome that we're seeking. So in this case, we split up the group in age. So everyone that's below 20, we go to one part, one leaf of the tree, and the other one goes to another leaf. And then we count in every group. So how many liked computer games in this group? Well, there was 2 people. So then we have a 2 there. And then the other group we count as well. So in this group we had 2 people that didn't like it, so it's -2, and then 1 that actually did. So that was plus 1. So we have minus 1 in it. And that is kind of a voting score. So then when we make a prediction, we get a new input, then we kind of use this tree model that we developed and see what is the vote. Do we have plus or minus vote? And then if we have plus vote, we would predict that this person, this input, likes the computer game. If we have minus, then we would say that he doesn't or she doesn't. But then trees are actually very weak predictors. They're not that good at predicting complex things. So how can we overcome this? Well, then there's this idea that came out in the 90s by this brilliant professor at Stanford, but maybe if we can add trees together and we can just kind of ensemble them. So what you do is you have your first tree. This is exactly the same tree as we had before, and then you add the second tree, and then with the second tree you also get the scores. And what you do then when you get a new input, so here we have input, we have first the score from the first tree, so that was 2, and then the score from the second tree, which was 0.9. And then we get the final score. And likewise for the other inputs. So that's the basics of decision trees. So now I will try to do a small demo on this. Kind of what we have been working on. Let's see here. So basically, here's the competition, and actually I should probably say a little bit about the competition setup. So the competition setup, since it's a time series competition, we always need to predict the future, so we don't have any data leakage. So the competition was set up so you have 1 year of data, you get 1 year of data, and then you are supposed to predict the next month. Here. And then you get, in the next task, you get 1 more month, and you're going to predict the next month. And that goes on. So we have actually now, just in the latest month, released the open source code under our GitHub. That is called Greenlytics and Decision Tree Forecast. And we have some documentation on that and how to use it. And basically I will try to run this here. So this is the only part actually that I will show of the code, but if you're interested you can go to the GitHub repo and look more. So basically this is what the code is doing. So it's first taking in the parameters that we want to use in our prediction, and then it's actually downloading the data that we are, or extracting the data from the data source. I have already done that, so I will comment out that for now. The second step is create features. So as despite from your networks in decision trees, you actually have handcrafted features. And that is something that I will also do beforehand. And of course, it's very domain specific. What type of features that you put in your model? Is it age? Is it degree, high school degree, or whatever? I will only look at this last part here, which is actually the prediction. So let me see. Okay, and then what we do is that we have an input file that looks something like this. So remember that I said that we had different parts of the competition. So, and this is actually what I specify here. So the first part is what we train on, and the second part here is what we actually predict on. So I specify this in my file. I also specify which features that I want to put in. which I believe are good predictors for this test set. I can also use lag features because actually decision trees are not temporal models, so to overcome this we can work with lags. And then to the nice things, so the interesting things are here. So this is basically where we use, which type of model that we use. And in this case, remember that I talked about these 4 different models. In this case, I decided to use a light GBM model. That was a model developed by Microsoft. I specify how many trees I want to ensemble together. And I specify kind of the methods of doing that and the rules that I want this to apply to, so the hyperparameters. In this case, this will take kind of a bit of time, so I will actually go with a smaller test, which is the same thing, but just I reduce the number of split sets to use 2. So let me see if I would run this then. So now it should use this right. So if I would run this, what happens is that it generates, hopefully, the data set, and then it predicts or trains, and then it predicts, and then it saves everything to a file. Which will appear, which will appear here in my repo. So here I got the file with all the different outputs that I want, but most importantly maybe the JSON file that I used to predict, so I can keep track of what parameters that I used to actually produce this result. And then we could have actually did a full prediction before today, so we can have a look at what that would look like. And I have a couple of notebooks to show you. So here I'm actually loading this data that I just showed you from the CSV files, used to plot it and play around with it. And I'm starting with just plotting the JSON file. So here you can see that we have all the full competition setup. And the features and all that. And then we can actually benchmark, because nicely enough, on this competition dashboard you had actually a leaderboard. So you had all the competitors and the score. So we can benchmark with them. And if we do that, we get this kind of graph where you actually see that with a very simple, non-optimized YTBM model, we get a second place in this competition. So actually quite good. So with some more hyperparameter tuning or maybe feature engineering, I think this could go all the way. Of course, there's someone that will say, but you looked into the test set.
No.
And of course, I did, because I checked this after I run it. But in the same sense, I used the exact same hyperparameters for every cross-correlation split. So I think that reduces also the overfitting. Just to have a quick view on what the prediction looks like. So this is what the prediction looks like. So remember, you want to predict the time series. This is the time series I want to predict. And then in blue you have the different quantiles that we try to predict. And what's interesting, this is actually for solar power, so it goes up in the day obviously and then down in the night. What's interesting to see is that in the days with kind of very high solar power, then it's more certain about it compared to the day with a little bit. And that makes quite a lot of sense physically, because in a partially cloudy day it's harder to predict what it will output than when it's very clear sky.
So commercially, what kind of time span is interesting to forecast? Is it 24 hours or just half an hour? Or?
Great question. So that depends completely on the application. So there's several different applications. One, for example, which I've been working quite a lot with, is power trading. And then you have market setup, where, for example, in Sweden you have the Nordpol market, which closes the day before every day. So at 12 o'clock we need to submit the bids for the next day. And then you need to actually do this before 12 o'clock for every hour next day. So it's 12 to 36 hours in that case. Okay, I was thinking to do a last demo, but I think I'm running out of time.
Last time.
It's fine, okay. So now I'll just show actually, so this is this is the open source code that we've been working on and how to kind of use it, but actually we've been also making a product of this. And that's what I will show you now. So this is a platform that we've been working on doing exactly this, but in a completely automated way. So basically, in the platform you can set up your sites, and this is just a demo case where we have a couple of sites in Sweden, and we will say here that we want to set up a solar site. So this is actually in Germany, so I will call it by that name. Let's see here, I need to remember here where I put the so here I have my cheat sheet. So the coordinates for this site, of course, so we know where to get the metadata from. So here you can see that we have a site in western Germany which shows solar panels, and we want to predict the output of these solar panels. And you can zoom out here and see that it makes sense, these solar panels are there, this coordinate is probably good. Then what we want to do as well in this case is actually not only using machine learning but actually using physical modeling, because we know about physics, so why not use it? So we can input some physical parameters like the azimuth of the panel, basically the orientation, the tilt, and also the installed capacity. And I think this was a specific case that had increases of capacity over time. So this is the current installed capacity, and if the installed capacity, so the amount of solar panels changes over time, of course our model will be confused. So we need to tell that to the model. So here we have a historical record of this. Okay, I think this was something like that. And then what we do is that we need to have a target variable that we're trying to predict, of course. So here we have just made a very simple drop-down sheet. So for CSV files, so here we have a CSV file with some with a target variable. So this is actually solar power output. This is some timestamps and the output here. And if we just take this and drag and drop, go through a small wizard, you see how it looks like, it seems reasonable, and then we click create. So what's happening now in the back end is that we are querying data for that specific location, and we're training a machine learning model, one of these gradient boosting models, and then we are then uploading this model and serving that in production. And when you have that model, you can actually see how it looks like in the end. So it takes a few minutes to do all that, but it looks like something like this. You have a prediction, you have the time now and a prediction forward. You have one prediction that's done with physical equations only, and one that's done with what we call AI then, the gradient boosting model. And this is served through API. So all this in the front end, you can actually do through APIs, creating the sites, uploading the data, etc. So that's a little bit what we've been working on, and the project on power forecasting.
Great, so much.
Yeah, thank you so much.
Exactly. So this is actually work that's been acknowledgements. So Swedish Energy Agency has been funding us on developing this research. So we are very grateful for that.
Great.
So any questions for Sebastian?
I have a question for you.
Sorry, Linda.
So I noticed that you imported the actual output in terms of what, right? But the weather input, where did that come from?
Exactly. So that's the magical part then. So the weather input is what we collect from outside.
Yeah, and you have a link up and running.
Exactly. We have a link up and running that collects this data, that version this data, and kind of make it ready so that we can train models on this data. So that's really the kind of the big cumbersome part that we take away from the customer, so that they don't need to care about all this other input data. They just need to care about this small CSV file or uploading this data through the API.
You just put in whatever location and you sort it out for the...
Exactly.
Thanks.
Yep.
Yeah, question. How do you charge for this?
So, good question. So what we do is that we have a SaaS model where we just have like a minimal fee, and in that minimal fee we have a number of sites. So sites per month, basically. So it's euros per site per month. Yeah. And then as you go with more and more sites, then you have a quite steep discount on the site per month charge.
Are customers ready for this? Are
Yeah.
they chasing you to buy?
Yeah, I mean, actually, this is obviously not the first platform for doing this. So what we are working on the innovative side is a little bit what I've been showing before. So most of these platforms are very closed. They don't say anything about how they work with the data, what they do with the data. And what we are providing to the customer is really a more open interface, where you can understand the kind of inner workings of the models that are used. And we hope that will bring trust to the decision makers that are using these tools to actually trust the forecast more and be able to use it in a better way.
Great.
So will this affect the energy price at the end, or?
Yes, renewables are definitely affecting the energy price. They're pushing down the energy price because they have very low marginal price point. And also, if you have forecasts that are wrong, that also affects the price. Yes.
I'll start with my favorite question. So how far have you come in predicting the weather? That was my favorite question.
So, I mean, that's interesting because, I mean, there's a paper that was published in Nature, the world's most famous science article, and journal, and that was called something like the silence revolution in weather forecasting. Because no one realizes that the weather forecasts are actually getting better, but they are. And they had a lot of statistical and data evidence that this is actually the case. So looking at models, how we predicted before and how we predict now, and they are actually getting a lot better. And of course, then our machine learning models are getting even better as well.
Great. Thank you so much, Sebastian.
Thank you.
So it's good to go from one type of energy solution, renewable, to another.
I'll apologize. I'm going to show code. I'm going to type code. So if I get it all wrong, that's fine. I have a challenge. I have to try and get it to compile in less than 3 tries. So, you know, if not, the beer's on me. Actually, no, it's on me. That's okay. So maybe to anyone who's seen me talk before, I've already actually pitched change detection at one of these events, and I think at the eBazaar as well, with my little lamp jump coming around, and I couldn't get it in, but I thought actually I'd show how simple it is, because I think that's actually the way to get it. But let's talk a little bit about what it is. First, well, there's no going back. You don't get to see who we are. Just to prove that it is all being done on the pipe. There is literally no going back on my presentation. So, what do? We are a startup that does machine learning for IoT devices. And that's why I'm using the Raspberry Pi here. That sort of fits into the middle of our range of devices that we support. And all of our algorithms, all of our techniques and everything are specifically for Internet of Things. So it's dealing with the real world. And this is a little bit different from the Greenlytics looking at big machine data. We're generally talking fairly small data sets. So my goal today is actually to show you that we'll train a model actually with data that we'll collect here. And I could do it all in 10 minutes, but I've been told I can chill out and relax a little bit. So we'll do this the slow way. We're not a very big company, but we've been around for a while. And we have a really impressive list of customers that we've proven our technology with, which is pretty cool. It's quite nice to be able to say we've helped reduce NOx emissions, or we make motors and bearings last longer, or we're really good for heat exchangers. I went with this beautiful piece of Lego because they actually hit me with an ad, and it got through my ad blockers, which is a little bit ironic because it doesn't happen so often. And I thought, well, I haven't bought Lego in years, and that's a really cool one. And it actually fits really nicely with our slide deck because we've got them all the way through, but it's also quite an interesting example. So, what do we run on? We can run basically anywhere that you would run on site. So that could be in a rack, You know, things like planes actually have racks of servers and stuff in it, surprisingly, all the way down to running on a sensor. And the version that we're releasing at the end of October is designed to run on really constrained devices, so Arduino class, M0, that sort of stuff. So in 3 months, I could do exactly the same demo running on an Arduino, sitting in the top here with nothing else. A little hard to plug the projector, you know, small problem. What we're going to do is we're going to train a model on some novel data, and then we're going to look to see if that changes. So I'm going to make this spin. It's very noisy, so we won't leave it going. And inside of here is an IMU, so it's the same kind of sensor you have in your phone. It's actually taken, it's from an Android phone, but it's hooked up to the Pi. We will read those sensor data, we'll train a model on it, and then we'll give a score as to how much change has happened. And then we'll do something to it that will cause it to change, something like a little earthquake, you know, something like that. To give you an example of what that could look like, this is actually from one of our tutorials. So if you go through our workbooks, which is a Jupyter notebook like you've just seen, you get to play with this data set, and it's electric motor. And you can see this is the temperature of the motor, and you can see it peaks off the top of the scale, so the temperature sensor actually can't read as hot as it gets, which makes it for a slightly more interesting challenge. But just looking at that, there's obviously not many features that are different. But when you train the change detector on it, it can actually tell the difference in response time, how quickly it's heating up, how quickly it's cooling off, based simply on the load. So it will look at how much the temperature has increased and how quickly it's coming down. Does that seem right based on the load? And it will give you a change score. So you can see in this one, somewhere around here, one of the bearings start to fail, and then it's completely done here and it's triggered a change. Fairly simple concept. Now, this is what I've got in my demo. Exactly the same kind of sensor. It's hiding in the middle here and running down and into the bottom of the pipe. We'll read it about 280 times a second, and we're going to read it in 3 different axes. So we're going to read X, which is this way, Y, which is that way, and Z, which is up and down. A little harder to demonstrate. And we'll end up with a graph like this. So this is 2 different axes. And you can see that the change that I made, it actually had no impact on the vibrations of one of them, but it had quite a significant impact here. This bump here is actually, it's really hard to put something on here without it detecting it. So that's actually the interference of me bumping it. But it then returns to fairly normal, and you can sort of see a little peak, and then over time it increases. Now this square graph is basically the training window, and it takes that long to be certain that something's changed. So we'll train it up, we then collect reference data, and then we'll start getting a change score. And once one of these is elapsed, then you can be certain that the only thing it's detecting is actually the change that happened. So my bump here would cease to be relevant by halfway through the next change point. Okay? I'm not going to draw a graph because it's a Raspberry Pi. We're actually going to look at the command line and the console interface, but that's basically what's happening behind the scenes. Okay, so we go here and we find a blank screen, and my mind goes wonderfully and beautifully blank. I started with a little bit of a template because obviously you have to cheat when you're doing these kind of things. So I've pre-initialized the 2-wire interface and also the IMU sensor that I've got on there. But then the rest of it's actually fairly straightforward. So we're going to do an outer loop, and I have a class called display, which captures a little button that's hiding down here that you can't see. And that's to allow me to reset it and also to allow you to break out. But as that's not actually really relevant to Swedish keyboard English key mapping, to what we're doing, I'm not going to worry too much about it. But what we're going to start off with is we're going to set up the parameters. So we start with our model parameters, and we're effectively training 3 different models, one for each of the different axes. First thing we're going to set up is the window size, and the window size is how many samples we're going to do. So it takes 2.75 seconds for the blades to rotate once. We're collecting 283 samples a second, and we want 5 rotations. So that's how many samples we'll consider to be a good training reference. You could do less, you could do more, but 5's a good number. Now we're going to set the sensitivity and the size of the features it's interested in. So, sensitivity, when I asked data scientist who was behind all of this, how do I explain sensitivity? It basically converts an infinite number into 1. which sounds kind of cool, but I think it's a little bit Buzz Lightyear. So the model that we're using will return a number from 0 to infinity. Infinity is a change, and 0 is no change. So it's kind of hard to work with infinity as a concept. So we have this factor called sensitivity, and it is literally a magic number, like pretty much everything in machine learning. But it controls how quickly the results will go towards 1 as the number starts approaching infinity. So for 2 of the axes, we're going to use 18 for that. And we're also going to set up a number of bins. And we're going to use 80. So that's basically saying we're collecting 80 different types of features, and we're going to look at how quickly the distribution of items in those features changes over time. Everyone knows in C++ you have to use semicolons. It's not about the indent. It's very clicky keyboard, right? That's okay with everyone. So we'll create our change detector, and we're going to just initialize it with those parameters. Never look at the keyboard. We need 2 of those, so we're going to do X and Z with those parameters. And then we're going to change the parameters slightly for Y because it has a different type of characteristics. So we want slightly different parameters for that. Set up a change detector for that, so exactly the same code. Right, now we need to create a display object. Initialize it. This is going to make that leaf go away. It's a leaf, not an apple. And we need to tell it the size of our window so it knows how to do a progress bar. That's super important. And then we're just going to do another loop on that. So we're going to loop around while the display is not interrupted. And then all we have to do is read the sensor values and feed them into the change detector and display the results. So we're reading these sensor values as raw numbers, so they're coming straight off the accelerometer, and we're not doing anything. We're not scaling them, we're not converting them to floating point, which is what you'd normally have. So it's set on a 8G scale, so the down reference, the Y actually returns 8,000 all the time, just to sort of give you an idea of the scale. The X and the Z will return somewhere between -100 and 100, depending on what's actually happening. So it's, fairly small numbers. So let's do X, Y, Z. And we'll just read into that, and it is, just remember my variable, LCM. And we just read straight into those. I'm not doing any error, never fails, it's a FIFA. How can it possibly go wrong? And then we just display it by doing the score. So we'll do change detector for each one. X, calculate score.
You're getting nervous, Melissa.
I will be in a second. Always return 0, right? That's not important. Right. What have I missed? So, while it doesn't, until it exits, set up the parameters, set up the sensitivity, create our change detectors, different parameters for the Y, initialize the display, this loop runs as long as the button hasn't been pressed, which means that I can reset the change detector and it will reinitialize everything. Read from the FIFO, and it's using the hardware FIFO on it because the timing, to make sure that we're always getting exactly the same timing and just remove some of the error handling. And then we do X, Y, and Z, X, Y, and Z. Perfect. Let's try it. Make. Oh no, it worked first time. That's amazing. And run it. So, our be really careful because it's a bit wobbly, so if I do anything I might upset it and we won't get a particularly good training. So the first thing it does is it collects samples to train it. The first window frequency, which will come up at 50%, is actually training the model, and then the next one is collecting the reference set. And once it's collected the reference set, then we'll actually start to see some numbers pop up on the screen. You can see a little progress bar on the back here. That is how much of that is trained. Now, I haven't got this running, so it's going to pick up red, because it's basically any tiny little vibration on the floor will pick it up. So now let's start our fan. This is an inverse generator. This is actually an inefficient fan that goes nowhere. Thank you very much for pointing that out. We're going to push the green reset button, and we'll train it up again. Now, be very careful not to bump anything, because the tiniest little movement will trigger. And hopefully we'll get a big green square and 3 green dots. And that will be the 3 dots at the top are X, Y, and Z axes, and the big square is the worst of them. So the middle one is pretty close to triggered, so it might be a little bit orangey. And that's probably because I'm a little bit too close to it. But you still will be able to see. If I change something, if I very gently put this mat on the back, you should see that they'll start to change over time, as it detects that that's a change in the characteristics of it. And that's affecting the Z, which is the up and down. And it will, over that change window, it will go red. And if we then remove that, it will start to re-establish back down to where it should be. And same if you put it in different ways. This is the tricky one, because it's the least likely to be picked up by anything. So this one might be a little bit slower in triggering the models, because it actually has very little impact on the actual vibration that's happening on the clasp. And so it's just slowly getting it on the Y, and a bit on the Z as well. Okay. Now what's kind of cool is that we'll pick it up in all sorts of different ways. So if we use a wonderful piece of paper towel, and we just brush past this, you'll see it goes quite quickly. It's probably quite red, isn't it? Let's wait for it to go back to green again. That looks pretty red to me. Yeah? So really, really simple. And you know, you could pick up stuff on the bottom, so I've got a little structural support down the bottom. We'll leave it for one whole window. So when that window percentage goes back up to 100, then you'll know that it's identified it as a different change rather than you just bumping it. But all I've done is just remove a tiny piece of Lego from the back of the stand, and that affects how it oscillates back and forth. And you can see it's returned on some of the axes from where I bumped it, but you can see it's definitely still high on Y, which means it's picked that up as a variation in how it behaves. Now, you know, we can retrain that really easily, so we can now say this is the new normal. That's fine. But you can see it's, you know, very simple bit of code, very generic solution. And it's not going to solve, let's actually just shut that off, it's too noisy. It's not going to solve the world's problems, this, but it can be a really easy way of adding a cross-check or some kind of extra safety which goes on alongside something without requiring a whole lot of change. So, you know, if we were to look at how much CPU this is using, it's using less than 11% CPU. And that's basically processing 1,000 readings a second on a little Raspberry Pi. It's using somewhere in the region of 150 kilobytes of RAM. So it's, you know, it's pretty low spec. There's quite a lot of the overheads actually updating the display and things like that. That's actually most of that CPU time. And this is the simplest type of change detector we do. We also have another one which will learn a pattern. So you train an incremental model as it goes, and we do this demo with a toy train. So the train goes around the track, and it learns how to predict where the train will be next, and then it looks for changes in the quality of that prediction. So if the prediction quality reduces, then it knows there's been a change. But for something like this, actually predicting where the vibrations are going to be is almost impossible, because there's not actually enough signal in there to get a prediction out of it, but there is enough to know whether or not it's behaving the way it would normally behave. So, like anything in machine learning, picking your algorithm is a really important starting point. But they don't have to be complex and fancy. So I think that's basically me coding on stage.
It's great. Do you have any questions for Melissa?
Will you do it next time with a blindfold?
Well, it's bad enough. So this is actually a Swedish keyboard, but I've got my key mapping set on US, so that's tricky enough. I don't think I need to go the next.
Sebastian?
Yeah, maybe you told us already, but which algorithm did you use? You said it was an important choice.
Yeah, it is important. This is using a KO divergence calculation.
Okay.
So, but the one we use for the train, we would normally use a very shallow neural network.
Okay.
Or a random forest, which might sound quite familiar to you.
Yeah.
It's basically a variation.
So and then you use kind of a probabilistic score and the KL divergence to train. So it's a probabilistic model.
It is.
And then the change is somehow a drift in the distribution.
It's actually it's exactly. It's a drift in the concept distribution. So
Okay.
if your sensor readings, if the distribution of your sensors change in a significant way, then it'll pick it up. Yeah.
Nice.
So this thing about doing IoT is you're so constrained on your device, so you need to use stuff which is simple and efficient, because you don't have a super cluster to run things on, you don't have a cloud. So we'll try and keep it as simple as possible, and yet get something that actually achieves a result that you could really use. So you could take exactly the same sensor and put it on a motor and look at whether the bearing is vibrating differently over time. And with just a little bit more signal processing, you put two sensors on, and then you can isolate it from banging on the floor or whatever other vibrations are happening in it. And it's really powerful, but not as complex as it might seem to be.
And you mentioned that you use only like 1,000 data points to train in this case, and then 1,000 to
I
do
think
the...
it's 273 times 280 times 5, so I think it's like 4,000, 4,500.
In that order of magnitude. Would it be better? Would the algorithm or the model be more performant if you use more data, or is that kind of where it caps out?
It actually, you want it to be enough to cover the normal stage, basically. So the oscillations on this probably don't exceed 2 seconds. So you could probably pull it down to that. But maybe you want to be able to pick up the longer duration ones. Things that don't help, if you don't take the high pass out of the accelerometers, that can make it quite noisy, because there's a little rubbish Lego motor in there which has got quite a lot of vibrations. And you don't actually want to pick up the changes in the motor's behaviour. But and that's actually, when I was doing this, I learned a lot about how you do that tuning, and it is a little bit like AutoML. And that you need to understand a bit about the problem domain and a little bit about the statistics in order to be able to come up with a good model. But because the actual code is really simple, it's not complex to do that. I'm not a data scientist. I looked at the formulas and went, oh, cool formulas, what they mean. But at the same time, when you get the data in and you start playing around with it, you can go, okay, I understand. This is how many different features are important or not important. And I might have needed to use a lag if this was more complex. My kind of ultimate goal is to be able to take this and put it on a toy train and show that exactly the same thing, the same code, could work for both of those problems, which really demonstrates that it is actually learning what's happening on that particular device. But it's a little hard to pull it out of the container. Maybe next time.
Alexander?
Yeah, do you have a personal favorite use case for this? Because I mean, obviously you can use it for a lot of different things.
I really, really, really want super intelligent lawnmowers, but that's just because I hate my lawn. No, I think of the things we've done, perhaps the least exciting one from a consumer point of view is probably the heat exchangers. And that is a change detector. We are monitoring the behavior of the, I don't even know, it's the output temperature, isn't it? I think it's the only thing we use.
Pressure.
And we use that to predict when they need cleaning. And it's so incredibly simple, but it makes such a huge difference to the amount of energy that's consumed. And, you know, we did calculations on it in conjunction with the company that makes them, and they were, you know, potentially saving a measurable percentage of CO2 emissions, because there are so many heat exchangers in basically every industrial process. And they all have exactly the same problem, which is they get fouled. But it's really, really hard to tell if they're fouled. And you could put sensors in that measure every single little aspect, and you could figure it out from that. But you could also just use what you already have and see if you have sufficient data from that to identify it. So I think that's, from the change to the sector side, I think that's the coolest one I've seen. So that was a super bad pun. Yeah.
Nice.
Any more question? Tell me, you have a lot of traction with Ekkono, you know, and I always guess because it's a quite modular, quite easy to understand offering. So do you see a lot of others doing similar things, or is this a wide kind of field for you to just harvest, or how does it work?
It's kind of a bit in the middle, because there are a lot of companies doing edge and IoT and things like that, but generally that's more around the tools and the training and how do you get a good neural network that will then execute on an IoT device. And I think we've sort of come from a different direction, which puts us kind of in a unique place. And that we're solving some of those problems which are really hard to centrally train. You know, it would be very, very hard to make a machine learning model of every meeting room in the world. You know, to get that reliable is a super hard problem. Whereas to learn in that room is a much simpler problem. So I think we're not alone, definitely, but at the same time it is still a very young emerging space, and that's really cool, actually.
So what's your business model right now?
License, library license, yeah, absolutely. Developer license and actually use and deployment on a device. But I think, you know, the amount of effort you'd save in writing your code and getting that to work, and the fact that you can add features to existing stuff really easily makes that quite attractive.
Wonderful. Thank you so much.
Thank you.
Alexander.
Yeah.
Yes. Jump to the next. This is the guy I think I've been in all the events. It's all the time.
It's possible.
Probably.
I used the oldest one I had. How sad is that?
We're using zeros.
Anderson.
Oh, sorry.
Yeah, I haven't opened it. I've only arrived at lunchtime, so.
Okay, so we're kind of in a similar space to Ekkono, but we have a different approach. My name is Alexander Samuelsson. I'm CTO of one of 3 co-founders at Imagimob. And I'm going to talk about a case study for Edge AI, where we're using our software tools, which we're offering as a service, to build an application which, with this application, you can detect hand gestures in front of earphones. And just a brief introduction to Imagimob. We're specialized in Edge AI. We've got experience from more than 20 Edge AI customer projects with some large Swedish corporations. And we offer Imagimob AI, which is a software tools as a service, an end-to-end solution for building Edge AI applications. And then, of course, we offer in-house Edge AI expertise. But just briefly, what is Edge AI according to us? Well, it's basically just about placing the edge, placing your AI models right at the edge of the network. And when we talk about edge of the network, we're thinking similarly to Ekkono, placing the AI model right next to where the data is generated and collected, right next to the sensor. By doing that, of course, you can create applications that are truly autonomous. They can react to things and their surroundings regardless of if you have a connection or if your connection is down. You can get a different level of real-timeness. So you can detect a change in your environment within milliseconds. But if you would have to send your data off to the cloud for analysis, that would be hundreds of milliseconds or seconds. And if this is sitting in a machine that needs to stop in order to protect itself or its operator, that's a crucial difference. But also by actually analyzing your data on the edge, you don't have to transmit it into the cloud. And by not transmitting data, you save a lot of power. So you can put your AI models in battery powered things, and you can achieve strong privacy. You only transmit the data that you need to transmit. What we are offering is a software service that guides you and allows you to build these kind of edge AI applications, guiding you from through the entire process. So starting with already helping you to capture and get data off of your sensor or edge device. And we do that through a tool we call Imagimob Capture. Then we have a PC application, Imagimob Studio, with which you can manage your data, divide it into different data sets. We provide a training service where you can get the data that you collected and annotated and transmit it to a cloud service, which helps you building and training AI models. Those results get transferred back to your PC application where you can evaluate and look at those models. I will show you how that works a little bit. And once you have something that you are really happy with, a good model, then with the click of a button you can optimize it for an edge device, and you end up with highly efficient C code, which you can put inside of our earphones, for example. So if that's edge AI, then what? And we have a solution to build edge AI. Then what can you do with edge AI? Well, there's lots of applications depending on what sensors you chose to pair with our solution. So if you put an AI model in a machine, you can create an application where you can detect anomalies and raise alarms or stop the machine if it's behaving erroneously. If you pair it with motion sensors like an accelerometer, you can understand human activity recognition. Or if you pair an edge AI with a microphone, then you can understand language and activate a device like Google Home or Alexa just when you're saying the right voice command, instead of transmitting all your private conversation into the cloud at all points in time. But if you combine edge AI with a radar sensor, which I'm going to show you today, and this is Ekkono. It's the smallest pulse coherent radar sensor in the world. It's really low power. And if you combine that with edge AI, then you can detect and recognize different surfaces and materials. You can detect deviations and defects in manufacturing processes. Or you can detect different kinds of hand gestures in front of earphones. And here's a video of my colleague, Johan. Let's see if we have sound there. Okay, well, what you can see here is that he's performing 4 different hand gestures, and they are being detected down here. And the radar sensor is located over here. And this entire application is running inside of this pair of over-the-ear headphones, and they are battery powered, and everything happens in real time, processed on the device. And we showed this in CES together with Ekkono last year, and next year in January we will show this but with in-ear headphones, same application. But to develop an application like this, you come across a lot of challenges. And I know that Magnus like to hear real-world experiences from projects. So I'm going to guide you through the challenges that we had in this project and how we solved it and integrated this into our software service. And the first challenge that you come across in any edge AI project, I would say, is, okay, you have a sensor or you have an edge device, how do I get the data from it? If it would be in a PC, you would just save it to disk, but now you need to get it off the actual sensor. So what we did here is we had the sensor dev kits from Ekkono, which has a serial interface. So we hooked them up to just a PC, and then we wrote a tiny Python application to transfer the data coming from the sensor off over Wi-Fi. And then we were set, and we had a scalable data collection solution because we have an Imagimob capture application for Android, which allows you to collect any kind of data over Wi-Fi or Bluetooth, but also collect data from the phone, in this case the camera. So now we had a solution that we could send off to Ekkono and different people to help us to collect data all over Sweden in order to get enough data. And here you will see why it's important to have the video, even though we're not using the video at all for training the AI model. So here you have my colleague Johan again. I recorded him using the phone app. He's performing the gestures. And here you have the raw, or some of the raw data coming in from the sensor. It's actually much more higher dimensions than this. You only see 6 out of 320 dimensions of the data. But since we had the video, from all the people collecting data for us, we could retrieve the data, and we could make sure that they were performing the gestures correctly, and that the quality of the data is high enough, and that everything is annotated correctly. So what you see here is that we've annotated the data so that we know that this is the thumb slide gesture, which appears here as an overlay over the data. So now we have a really scalable data collection solution here. But then we come across the next problem, which is pre-processing. And I think you touched on this about manual pre-processing versus learned pre-processing. And our problem here is that we have a device which is generating a lot of data. It's generating roughly 30 kilobytes of data per second. And we want to create a really small AI model because we want to translate that into different gestures and detect them quick enough so that you get a responsive earphone when you want to switch a music track or answer a call. And we are talking about deep learning here and neural networks. That's the kind of the models that we support in our tool. So if we would just train this like you normally do when you build a deep learning model, then you would feed it with the raw data from the sensor and let the model learn the mapping from raw data into one of these gestures. There's two problems with that. First, it takes a lot of data, which takes time and it's expensive to collect. Second of all, you end up getting like a large chunk of the model dealing with this very small, high frequency or minuscule features of the data. So we had to create a library of different pre-processing functions so that we could put that in the beginning of the network in order to create a smaller network. So basically reducing the data from the radar while still preserving the important information in it. But the good news is that we integrated this into our tool here, the Imagimob AI tool, which means that we can piece it together like Lego bricks. So it's very easy to add a new pre-processing layer. You can combine it together in different ways and configure it. And also, the users of the tool can easily add their own pre-processing layers. And by doing it this way, what we're actually doing, we're combining it with the network, so it's just like a layer. So we have, now at this point, when we've built our pre-processing, we have everything that we need in order to send this to our cloud service and build a fully functional AI model. And we can just change some parameters and we can start a new job and experiment with it really quickly. Okay, so now we have everything that we need in order to start building models. Then comes the third challenge, which is testing and verifying. And testing and verifying edge AI models is a real pain, because to test on device, you would have to go all the way to C code, and that's quite easy in our tool, which you will see soon. But moreover, you would have to, in this case, reflash all these headphones that we've shipped all over Sweden with the new firmware in order to actually test this model. And to get a really good test feedback loop, you probably want to do this like several times every week. So it's just not feasible. So what we created and integrated into our tool is the ability to, as you're building these AI models, to run them across all of your data that you have collected. And what's really powerful here is that we collected the metadata, so we have the video still, we have the raw data from the sensor, and we have data here from more than 20 people in different locations, and we can just play it back like it's a regular video, and look at the raw data, look at the raw output from the model, but down here also see the annotations that the model makes on top of the data, the predictions. So what we have here is the ability to run a field test with 20 people in front of your PC and see exactly how the model performs here. So here you see when it detects this thumb slide gesture that you want to perform. And then, when you've really tested your model like this, then you can convert it into C code and deploy it to your headphones and get a feel for yourself exactly how it works. But then you know that you have a model that will probably perform really well. And when you are at this stage, it's really just a click of a button to translate this cloud model into highly optimal C code and verify that it's functioning correctly. And this entire application runs on an ARM Cortex M4 processor, and it's using 80 kilobytes of flash and roughly 20, I think it says it, roughly 21 kilobytes of RAM. That's what I wanted to show. I can show you a live demo on my computer if you want. And please sign up for a free trial, because we're offering this end-to-end solution if you want to start experimenting building your own edge AI applications. And also we are hiring, so if this looks like something that would be fun to work with.
Excellent. Thank you. Any questions? I know
I
that
have a
you
comment.
changed your...
Yes, I think this is pretty corona suitable, right? Touch-free way of, managing stuff.
Yes,
Has that affected you in any way, in a good way then, I hope?
the
Have you seen
corona.
any new applications of this solution?
The interesting thing is that we just started this free trial, this early access program. So we did a smooth start right before the summer. So we have 2 paying customers using the tool right now. But then we have this early access program, and 3 of the participants, 3 different companies in the early access program, are building applications using this radar, and it's all gesture. But they are adding their own gestures instead of using our pre-created ones.
Brilliant. No, I happen to know that you changed your business model quite radically.
Yeah.
And I think that's so interesting because you're one of the pioneers in edge AI and all these things. And can you just tell us a little bit of why and how you changed your business model? Not to me, I know.
Yeah, no, but our business model used to be that we were running all of these projects end to end for our customers. And I mean, we would get paid by the hour, and then we would get paid when they deployed. So we would get an amount of money for each device that were being sold. And I mean, there was 2 problems with that. I mean, first of all, it doesn't really scale until late in the future, and you have very little control of what actually gets deployed. So we had several successful projects, and we have one application that is actually, you can buy it. It's a watch for the elderly, detecting falls. But many of the projects that we ran, even though they were successful, for some reason or the other, they weren't deployed. So we realized, we need to scale this, and we need to actually make good business, even if they're just using this for research. There's still a negotiation where we can get money per device. And it ends up being cheaper for the customer too.
I think it's so interesting because in the beginning of a wave of a new technology, people don't know what they want. That's when the traditional model is dangerous.
Yeah.
But, so this is a much better version, but the other model will be there when customers get to know what they want. I think it's brilliant. That's excellent. Okay, up, Sebastian.
Yeah, just curious, what is the business model of the new, how do you charge for the system? You have a free trial, so it's a premium first, or a trial version?
Exactly, you get to try for a month, and then you pay per user.
Okay.
So it's a monthly cost.
And then you can deploy infinitely many models, or is there a limitation to that?
So you get the right to, when you're deploying commercially, it's a negotiation.
Okay.
But then we subtract, everything that we've paid already using the service.
I see.
So you don't pay twice.
Another interesting observation for all of you is that it's all about data to train the models. All the 3 of you have talked about that, and it's all the thing. Algorithms is great, but without data it doesn't matter. So
yeah,
this is I remember your video when you were falling. Where did you watch? You were throwing yourself in the gym stage, whatever, to see how you can fall in different ways. And it's really complicated to get the data.
Yeah, creating that watch, I think I've fallen on mattresses 2,000 times or something. if I don't make sense, that's probably the reason.
Okay, we're done there. Thank you so much.
Thank you.
So, we actually we have made a real event. It's a small event, but with great people, so who cares?
Very good.
And the other part of this is obviously we have a good chance to talk to each other and check out and so on. So as we say, we close at 9 and not before, so please feel free to stay. Nobody on the video will see how many we are, so or who stays, so we don't ignore that. So thank you so much for coming, brave people, and thank you for presenting, and enjoy yourself. And by the way, we have our next real life Get on Top of event, the 6th, I think, of October, on 5G. That's a new topic, so it's the first one. So, and there are limited amounts of seats, so sign up quickly, please. Thank you.
Thank you.